Okay, today we're just going to take a quick look at area between curves. So a couple things. Before we jump into looking at areas between multiple functions, let's just go back and I want you to think about how we add up area under a normal curve, just a regular old curve. So what if we want to find the area under the curve f of x equals e to the x from -1 to 1? Well, we know that's just a definite integral, right? That's easy to do. Here's a good way to kind of think about this, though, and this prepares you for the stuff we're going to do today, but even more so it prepares you for the stuff we'll do like after today when we're looking at calculating like volumes of rotation and revolution. It's really useful, and next year when you're doing multivariable calculus and you're adding up volumetric integrals, it's really useful to think of integrals as adding up little small pieces of something, right? So like in this case here, we're adding up an area, we're adding up pieces of area, right? Well, what do the pieces of area look like? We're familiar with this. They just look like little rectangles, right? So if we add up a large enough number of these rectangles, as we did with Riemann sums, we get an exact area, right? So each of these rectangles, the height is determined by the value of the function, and the width dx is approaching 0, right? So in effect, we're adding up a number that approaches infinity, right? So then when we add up our integral, well, we know that our limits of integration in this case are from -1 to 1. But what are the little pieces of area looking like? Well, the height is going to be determined by, this is just going to be, if this is our function f of x, then the height is just going to be, this distance is just f of whatever x value we're interested, wherever we are at the moment, right? Like if this is the x value, the x values are going to vary from -1 to 1, but for each of those x values, there's an infinite number of them, but there are an infinite number of rectangles we're adding up. The height is just f of x, and the width is just dx, right? So each of these little pieces here, f of x dx, that just represents the area of an individual rectangle. Okay? No big deal, nothing profound there. But that sets us up to add up areas between curves. And this is no big deal. You guys have done a bunch of problems like this already. This is really not a big deal. If we want to find the area of the region bounded by the graphs of these two curves, f of x and g of x, well, all it is just going to be the height of the big rectangle minus the height of the small rectangle, right? Doesn't that make sense? So another way of visualizing that would be to say, well, the height of the rectangle is just going to be the top function's value minus the bottom function's value at any value of x. And again, we're just going to add those up between our limits of integration, and there are going to be an infinite number of those, right? So then this ends up being the height. There's the height of the rectangle, right? That's this distance. And that's just the width of the rectangle. No big deal, okay? From whatever A is to whatever B is. It makes sense that if we want to add up a positive area here, though, we've got to make sure that we've got the curve set up where we're subtracting the bottom curve from the top curve, where I'd get a negative area, right? Because our convention is we add area up from left to right and bottom to top. Does that make sense? Like if I flip this around and did integral of g of x minus f of x, I'm going to get a negative answer because I'm adding up the area. I'm not adding up the area below a curve. I'm adding up the area above a curve. Give me thumbs on that. Does that make sense? Okay. So let's set one of these up then. Like if we wanted to, how am I going to set up this integral? If I want to add up the area of the region bounded by f of x equals e of x and g of x equals the square root of x from 0 to 1, what's that going to look like? Integral of what? What's that going to be? Okay, so the limits are from 0 to 1 of what? That's it, right? E of x minus square root of x dx. And that's a pretty easy integral to do, right? We can calculate, we can split it into separate terms and do each of those integrals and get an answer. I'm not even going to bother with it. I mean, that's no big deal, okay? All right, moving forward. Okay, what about a problem like this now? This is a little less specific. They're saying find the area of the region bounded by the graphs of f of x and g of x. Now, they're not giving us limits of integration. So what do we have to do to find the limits of integration here? Got to find intersections, don't I? Because a bounded region means it's a region that's completely enclosed. That's what that definition means, right? If it's bounded, it's got to be contained, right? There's only one part of the region that's formed by these two curves that's completely bounded. If I go to the right of this intersection, they're never going to cross again. So this is an unbounded region, right? Unless I impose a boundary over here and say, add another line like x equals 10 or something, then I would enclose a region, but that's not being done. Same thing over here. The blue curve will remain below the whatever color, magenta curve forever when I go to the left from the intersection at -1, right? So I would have to find the intersections, and that would mean just solving a pretty simple quadratic equation. If I set these equal to each other, 10x minus x squared equals 3x minus 8. What would we do? We just push everything. We want a positive number of x squared, so we just push everything to the right here and put it in standard form. So I'd get x squared, minus 7x minus 8 equals 0. Solve the quadratic equation the easiest way. This would just be, I'd just solve by factoring, right? I could find magic numbers, -8 and 1. And so that's giving us our solutions, x equals 8 or x equals -1. Right? And we don't even need the y coordinates. We just need the x coordinates. And then we just set up our integral, right? And the integral is going to be no big deal. Area, what's that one going to be? Daisy, help me set up this integral. If I want to find this enclosed area, what are my limits? -1 and 8. Okay, and what's my top function? There you go. And I could, if I want to put that in parentheses, I can. It's not necessary. It doesn't do anything. Minus what? Okay, and that's got to be in parentheses, doesn't it? Because we're subtracting that complete function. There it is. Easy. Simplify the integrand, integrate term by term, piece of cake. No big deal. Okay, here's another one. I mean, we don't really need to even do this one, right? If we're trying to find the area in the first quadrant, right? When they say in the first quadrant, that just means we're going to be for values of x greater than 0, right? Bounded by these functions. Again, we just find a point of intersection. If we set these curves equal to each other, how do we solve that? I mean, you can just reason through that in a way. If you're thinking in quadrant 1, now it's coincidental that this happens in quadrant 1 of the unit circle. That doesn't mean the same thing. We're talking about quadrant 1 of the xy plane. But if I do think about the unit circle, where do sine and cosine equal each other? Where are their values equal? Pi fourths. And then again down here at what, 5/4 pi, they'd be the same. But this is the one we're interested in because that's a negative value, right? Or it's a it's going to be, I mean, these are going to meet again, right? But we're only interested in the first bounded region is what they're talking about, right? The first point of intersection, there we go, which is going to be at pi fourths. So that's how we find our pi fourths. And then if we set up this integral, would everybody agree that the area is just going to be the integral of the top function? For that portion where we're looking at the bounded region is going to be the cosine function. Bottom function is the sine function. And we're just going from 0 to pi fourths, and that's no big deal. Again, pretty simple integral. Okay? Okay, so when is this going to get a little more challenging? Slightly more challenging. If we want to find the area between a graph and the x-axis. So what's being implied here? We're talking about kind of a net area here, right? We want to know, in other words, think of it as if I were going to cut out a cardboard shape like this, what would be the area of that shape? So we're going to reckon all area to be positive here. Because normally this would, like if we're just applying the fundamental theorem, this a sub 1 would be negative area, right? Because it's below the x-axis. So if I just did a straight integral of f of x from 0 to 5, I'm going to get a little bit of cancellation, right? What do I need to do if I want to calculate the net area, so all the area is considered to contribute positively? Got to split it up, right? Again, I've got to just find the zeros of the function. And we know that if I set that equal to 0, I'm getting zeros at plus or minus 2. Well, the only one we care about, because we're between 0 and 5, the only intersection on our interval of integration, right, between the limits of integration is at 2. So we'd have to do 2 separate integrals here. Now, you can do this a couple ways. We talked about this earlier. One way to do it would just be to put absolute value bars around each of the separate integrals, right? You certainly could do that. So we could write this out as the net area equals the absolute value of the integral of f of x dx from 0 to 2, right? So we're just looking at this piece, plus the absolute value of the second integral, right? You can do that. That's fine. You're going to get the right answer. If you don't want to use absolute values, sometimes we want to avoid that. We could alternately just make sure that we're always defining the areas with the top function first and the bottom function second. So without absolute values, this would just look like the integral of, what am I going to have in here? If I don't want absolute values, how am I going to define that area? See what I'm getting at here? It's going to be the opposite, because it's going to be, essentially it's going to be the area defined by the top function is the x-axis, which is just y equals 0, minus the bottom function, which is f of x. Well, 0 minus f of x is just negative f of x, right? So we could just do that. Right? And I don't need absolute values. Okay, give me 1 to 5. Is that making sense, what we're doing there? Okay. Any questions? Okay. Take your pick. Either one of them works. Okay, so now shift gears a little bit. So what happens if we've got non-functions? Or, well, we have curves that are not functions of x, but are functions of y. How do you know if they're functions of x? If I go back, why, just quick reminder, why is this a function of x? How can we tell? Because it passes vertical line test, right? Okay, so how would we know that either one of these are functions of y? What test do they have to pass? Horizontal line test, sure. Okay, either one of these curves only ever intersect a horizontal line one time, right? So we're fine. If I wanted to add up the area by partitioning the y-axis, I'm just doing this a little bit differently. Now I'm adding up the area instead of below curves. What does below mean in a sideways sense, right? If we're talking about functions of y, where this is our independent variable, now we're looking at the area below, meaning to the left of the curve, right? Does that make sense? So when we partition this up then, our areas are going to be built from horizontal rectangles. Okay, this time the width of the rectangle is given by dy, and the height of the rectangle is going to be the rightmost function minus the leftmost function. Okay, that make sense? Otherwise, it's exactly the same as we were doing before. We've just turned it as all. So here's the way we're going to add up area. Let's look at an example. So what about something like this? What if we want to find the area of the region bounded by the graphs of f of y, which we fancy name for x this time, is equal to y plus 2 and g of y equals y squared? Well, if I look at graphs of those, I can see that the bounded region, there's only one bounded region, and in the top function, meaning the right function, the rightmost function, is going to be the line, and the parabola is going to form the bottom of that area, right? Meaning the left is the leftmost function. And again, I would just have to find intersections, but that's easy to do. This time, my input variable is y, so I'm solving a quadratic equation in y. I want to know the y values of the intersections. So I would just be taking y squared equals y plus 2, so y squared minus y minus 2 equals 0, y minus 2 times y plus 1 equals 0. I can factor that pretty easily. And that's giving me y equals 2, which is right there, and y equals negative 1, which is right there. There are my limits of integration. Okay? Just takes a little bit of getting used to that we're looking at partitioning along the vertical axis this time. And what would my integral look like then? Caleb, what's my integral going to look like here if I'm horizontally partitioning this? What are my limits going to be? Negative 1 to 2. Good. Good. Instead of going left to right, we're going bottom to top. And what minus what? There you go. Y plus 2 minus y squared dy. Big deal. Now we just flip into calculus mode. It doesn't matter that those are y's. We just do the integral. Okay? Okay, so what about one like this? Now, these functions are one-to-one functions, right? Meaning these are functions of x and y. Make sense? Both of these pass both the horizontal test and the vertical line test. At least the parts that are graphed here, right? And that's all we really care about, are the parts that are actually enclosing the area. If they're non-functions somewhere else, we don't care. So we'd have an option. We could do this either way. In the intervals we're interested in, either of x or y, they both pass horizontal and vertical line tests. What if we partitioned this one vertically, like we normally do? We can do that. How am I going to have to set this integral up, though? If I want to find the total area enclosed in quadrant 1, is that what we're saying? Yeah, by the x-axis and these two functions. How am I going to deal with that? Okay, so what's that integral going to be? My total area then is going to be the integral from 0 to 1 of what? Minus square root of 4 minus 4x. Okay, good. Plus integral from of, say it again? Yeah. Okay, good. Everybody get that? So if I were doing this integral, then I could maybe rearrange this a little bit and make this a little more convenient. I can integrate this one term by term, right? I could split it into two separate integrals. And if I do that, I get a total of 3 integrals, right? Well, I don't want to spend too much time on this, but if I split this up, if I write this out as a sum of 3 integrals, I'm getting the integral of square root of 4 minus x from 0 to 1. Let's write this one next, plus the integral of 4 minus x dx from 1 to 4 minus the integral of the square root of 4 minus 4x dx from 0 to 1. So any way I can make that a little simpler? What about the orange ones? Yeah, right? That's one continuous integral, isn't it? Right, so I could write all of this as the integral from 0 to 4 of the square root of 4 minus x dx. And I would just integrate that with the u substitution. What would my u be? Four minus x, yeah, okay. Plus, or minus, I guess, minus the integral of square root of 4 minus 4x dx from 0 to 1. And again, I'm going to do a u substitution there, right? If we have time, we'll come back and do that, but I want to make sure we get the theory down here first. So look what we did there. That's actually a little bit profound. If we're adding up the area under the orange integral, that's going to be this, everybody agree, that's going to be this integral, this area right there, right? Okay, minus the green interval. Well, isn't the green interval just this area? Right there? So it works, doesn't it? We just found the area by subtraction there. Another way we could do this, right? Okay, give me 1 to 5. Does that make sense? Okay. I mean, we could have even just looked at this and said, you know, I could add up this. I could have just done that directly and just jumped right to that integral too, if I weren't actually just partitioning. Okay. Is there an easier way to do this one? Do I have to, like in this case, no matter which strategy I took, I had to break this thing up into 2 separate integrals. Is there a way I could have done this without having to break it up into separate integrals? Like I had to have an orange minus a green, right? No matter what I did, or I started off with this blue integral plus another blue integral. I had to write it as 2 separate discrete integrals. Could I do this as a single integral? What do you mean? Like combine the functions in a way? I don't know how to do that. Maybe there's a way to do that. Could I just choose to slice it differently, though? What's that? I did go vertically. Horizontally, how about? Right? What if I slice it horizontally? Then I only have to do one integral, right? Because then there's only a single, a single integral defines one consistent top function and one consistent bottom function, right? So if I'm partitioning using the y-axis, if I'm doing, and the way I want to talk about this is either vertical slicing or horizontal slicing. If we're going to cut this area up into horizontal slices, this is a little bit easier to do. Well, okay, maybe it's not easier to do because I actually have to rewrite the functions then, right? They're written as functions of y now. I would have to solve these for x, right? That's not a big deal, though. What would I do to rewrite this function in terms of x, to isolate the x? Square both sides. So that's going to give me 4 minus 4x equals y squared. I could subtract the y squared to this side and add the 4x to that side and divide by 4, and I get x equals 4 minus y squared over 4 is one of my functions, right? Okay, and that's the blue one, so that worked out well. And then this other one, I do the same thing. If I square both sides, I get y squared equals 4 minus x. So x just equals y squared minus, or sorry, 4 minus y squared. Right? But once I've done that, now that I've written these as functions of x instead of functions of y, it looks like they did that anyway, right? So I got my colors backwards, didn't I? Yeah, I got my colors backwards. That should have been the blue one and that should have been the pink one, right? But you get the idea, okay? So then I could just set this up as an integral of the horizontally top function, so the rightmost function, which is this one, minus the leftmost function, which is this one. We'll write it as 1 minus y squared over 4, how about? D what? dy. And what would my limits of integration be? Yeah. Now we're going bottom to top, and we just go 0 to 2. And that's an easier integral to do, right? I can combine these terms, and this is just a single polynomial, which is an easy thing to integrate. Okay? So I guess what you pay for here is you've got to solve for x, but the benefit is I get a single integral, and it's a polynomial. No u substitutions, none of that stuff, right? If I slice this thing vertically, man, I've got integrals that aren't horribly hard integrals to do, but I am going to have to do some change of variables, some u substitutions to get these things to work, and I've got 2 of them. Okay? Which is better? I would say slicing horizontally is better. It fits the function better. Okay? All right. So last one. Man, we got through that pretty fast. So try this. Bust out your TI-84s and try this. Let's just assume for a second that you try actually doing it on the TI-84s. Just because like on the AP test, that's what you'd have to use. Maybe in college, that's what they're going to make you use. You better get used to them a little bit. Okay, what's this going to look like? So what do we want to do first? Graph it, yeah. Okay, there's one function. To graph this one, I'm going to go ahead and I'm going to use the fraction template. Remember, to get to the fraction template, I can go alpha F1, enter. Okay, just quick reminder, when I want to start a graph here, I'm just going to go zoom standard, so zoom 6. And we can see the points of intersection, there they are. To calculate the points of intersection, remember what you have to do is you got to go second, calc, and then I go 5, intersect. And then it wants to know, is y1 the first curve? Enter for yes. Is y2 the second curve? Yes. It wants a guess. So I can either just manually trace over to it, or I could type in an x value. You just got to get close to it. Okay, so there's one intersection. I'm just going to take a picture. So there's one intersection. I got to repeat the process. So I go second, calc, 5, enter, enter. And then this time I'm just going to make a guess. I'm just going to type one in. I'm going to type in 2 because that's pretty close. So I can just type in x equals 2, enter, and it gets me to my spot. And there's my other intersection. Okay, now that I've got my, I guess I wrote those down. You would write those down. Now, how am I going to find the area between those curves using technology? What would I do next? You can, yeah. So we'd go math. I'm going to go number 9, which is finite integral. And how come it's not? Okay, there's 2 ways to do this. So that's not it. Hang on, I'm in the wrong spot. I got to get, get out of the graph. Let's try that again. I go math and I go 9. There you go, that looks better. Okay. So my limits are going to go from the bottom limit we already found was negative 3.07564 to my top limit of 1.408973. Now, what's my integrand going to be here? Yeah, okay, good. X plus 10 over 3. So alpha, I'll use that cool little fraction template. Oops. Minus. Now I got to be sure to put this in parentheses, right? I've got to, because I'm subtracting the whole quadratic function. So in parentheses, I'd have my x squared plus 2x minus 1. And then it's dx. And there it is. That's my area. On the AP test, they just tell you got to round everything that's numerical to 3 decimal places, so it'd just be 15.032. Okay, good. Questions? Okay. I started doing something yesterday that I think will be helpful. I'm going to go back and try to do all of the sapling problem sets this way. If you go into Plan Book, it's an easy way to get to this. If you go into Plan Book and you look under, I got to make some new templates for us. If you go into Homework Solutions. Look, I've got a new folder in there for Sapling Chapter 7 Homework Solutions. And then if I pull these up, you can't see that, yeah. Whoops. So again, if I go into Homework Solutions, Sapling Homework Solutions, I go into Chapter 7, and then I pull up one of these, like 7.2, for example. There are the 7.2 solutions. So it tells you, the way I'm going to set these up, they always show you for the problem number on the sapling assignment, it's telling you what the book problem number is. So problem 1 is actually 7.2, number 3. Problem 7 is 7.2, problem 29. And then down here, I've got they're referenced by the actual textbook problem numbers. So there's number 3, that's the first problem, and it just gives you, I just created little PDFs of the solutions for all those. So that's a little more convenient than having to hunt all those down in those huge solution manuals. Okay? All right. Go. Work.